Okay, welcome back to making a compiler, to making a little language to generic types. This is part 2 of the generic type journey. We're trying to make this program compile. It has a generic struct in it. We got this far, and I think we need to specialize this type. So I think we're going to pull out a function. And we're going to go ahead and do that. And we know it's going to need to know about what we passed in, these eval type params. If you're lost, go watch part 1. And yeah, type ID is our new function could probably take care of checking if it's generic. So, all right, let's jump down here. Specialized type. Uh-oh, Copilot's on. Maybe not tonight. Okay, so what I had said is we're gonna take a slice of type IDs. This is a type params. Type application. We're not actually going to take this, but parsed. There's a parsed type application, yeah. And the actual type ID. Type ID. And we probably need to know our scope. Actually, are we doing it in the context of a scope? Maybe we are, maybe we aren't. And this is going to give back a type ID. Okay, and let's move our generic check. But yeah, I don't even want to evaluate the type params if it's not generic. So yeah, maybe we do it here. And then that can just be an assertion. We could assert that it's generic. Do a debug assert. If that becomes a problem for specialized type. I'm drinking a lemon elderflower soda from Trader Joe's. I feel like you always have to divulge or people will just be wondering, what's in the cup? Is it water? Is it tea? Okay. So we don't want to pass the type application. What we want to pass is the mapping, something to be zipped up where we have the type IDs and we have the params. So it's really the params that we're interested in from the type application. Yeah, I want to know their identifiers. Because essentially what I need to do is take the fact that a type was provided here in the position of t. So I need to map this up to, I guess, really the type parameters of the original definition. Which I didn't really capture so well. I actually just stored this as a struct that happens to have a type variable here. Maybe that's fine. I just don't really know what to call t. So I'm a little stuck again. The other option is to rerun the evaluation of this actual AST node, substituting in what we know t to be, which would reuse a lot more code and might be just fine. But I'm not sure if that works. If that always works. So by keeping yeah, one of the things I said I need to do is ensure the correct number of parameters. So what am I comparing this to? I know how many params were passed, like on this type application. And I've in fact already evaluated them. Where do I say how many type variables my type has? I think I'm missing an entire notion here. On my type, enum type. So what I did for the generic struct is I just put one in here where one of its fields happens to point to. And I do know how many type variables I have. I put them in the scope of that type defin. But I don't have a way back to that type defin. So when I evaluated this, I did put a type variable t in scope, but I think I want more like rigid evidence. So it's almost like I have a new type of type. I could do it this way. I could say, well, really what I have here isn't actually a struct. It's a way to make a struct. It's a function that makes a struct. It's a generic. So at the risk of using the term generic, or we could just say, to mirror our type application, we could say we have like a type function, or just a generic type. But we could say a generic, for lack of a better word, and then we put a generic type in here, which is going to be a struct that we get to define, and it's going to have a type inside, and we're still going to have the struct, but it's just going to know a little bit about its type parameters and maybe store their constraints as well. Because I didn't have a place to keep those either. The constraints, I definitely didn't pass any. I'm not even sure if that was on the type variable. Does type variable have constraints maybe? Yeah, I put it here. Yeah, so there's actually a type ID for each of the type variables too. And I could store that in the generic that I have. So we have this, and that could just be params, I guess. And that's a vec of basically we want, I think I want the names and the type ID of the type variable I ended up using. And then type variables know about their own constraints. So constraints is for when we want to be able to say, hey, T has to be hashable. Inner. And you know how I talked about needing to cache whether a type is generic? Well, haha, we don't need to do that. We don't need to go find out if a type's generic by walking it. We're just gonna have them here. If a type's generic, then it's wrapped in this thing. Because we needed to preserve this info anyway. And generic types. The question now is where do I attach the definition info? Is it on the inner struct that happens to have a type variable in it? Or is it on the so-called wrapper? And does this mean that if I do an opaque, it's actually going to create three types? The inner one, the generic, and the opaque wrapper for the generic? I don't think you can have an opaque generic. I'm going to make this a no commit. you have an opaque generic. I can probably answer that once we finish this feature. I can't answer it now. Okay, well, let's just start with this. And now, since we added a type of type, we've got some boilerplate work to do. Unfortunate. Let me go ahead and I'll regret this being a tuple. So we're going to call this generic type param. And this is going to be name type. And this is going to be a generic type param. And now I'm just going to walk through the errors. So for a generic, what's its AST node? I didn't give it any. Is that a mistake? Its inner type will have one, or might have one. And that's kind of what I'm banking on. Okay. Why not? We'll put it on there. We can put it on both. Maybe we'll do that. The defin info, though, probably, yeah, I still can't decide. The question is, how will it be used? So the defin info. I think it goes on the generic. So this definition info, we have a lot of types that aren't part of like a type definition up here where you give it a name and stuff. And so those don't have one, but types that are declared like this do have one. And all it is the name that they're declared with, the scope that they're declared inside, and whether or not there's a companion namespace. A companion namespace would be if I made a namespace in the same scope here, I can do special things in here that relate to the type or box. That's how methods are created and some other things too. Is type generic? Well, this is interesting. That's gonna be a hard yes. The question is, so this is used. It's not really the same kind of generic. So this is a type that's yet to have its parameters applied, versus what I'm checking for with this function usually is have all of the type variables for this function been accounted for. And I'm trying to decide if I should specialize the function or not. So if I go to the usages of this, the really important one is right here. So this is deep in our specialization code. And I say we skip specialization if any of the type arguments are type variables. Because we could just be evaluating a generic function that calls another generic function, in which case we don't actually want to generate a specialized function. Otherwise, we end up with a function going to CodeGen that still has type variables in it. So that's what this function is being used for. So I'm going to walk this back and say, does type reference type variables? It's not really is generic, but so much as is fully concrete or something like that. We'll just say that a generic type always does, because these probably shouldn't leak through. We should have applied the variables to them. This is really just like a tool for us. Like these won't really appear. Like a function won't return box. It'll return box event or box of t, right? In which case it won't be generic anymore. It will have been applied. Even if it's been applied to be a type variable, we won't have this type anymore. We'll actually have like struct. It'll just happen to have a type variable as one of its types. That's at least my plan for this. Item type of iterable. It's not an iterable. Well, yeah, these don't really work like the rest of the types. It feels kind of bad because each of these I'm getting to, I'm like, oh, this doesn't really participate in the same way as the other variants. It's not just that there's none. It's like, oh, well, it could be iterable. The thing that it wraps could be iterable, but this isn't. You're not going to be working with these. You're never going to have a value of this type. I'm going to do it anyway because I don't know how else to get generics working. Okay. Yeah, so this can be to do. Sorry. Just going to try and get all the red gone so we can think clearly and get ready to go. So specialized type. I must not have? Okay. Yeah, well, if you don't take self, then it's not going to show up. So at least it's there. So if we have a type application and we look up the type in scope, we should expect it to be generic. And so this is actually going to be types.get let type generic else. I'm going to early return here. Now I'm just going to peek down to the bottom of the function and make sure, yeah, that won't cause problems. Okay. All right, I gotta make a note. At 18 minutes in, coughing. Okay, so I'm gonna do a little trick here. I'm debating making all of this part of that, and it's really just handle type application. Because it's hard for me to factor this out of the context of where we are. I'm not really even sure what to pass to it. Let's focus on this for now, though. If we were able to do this, then, okay, so the specialized version has been added. I think this is all we would need to do to have evaluated this type application. Yeah. So I'm going to be like, self eval type application. And we'll, yeah, we'll take the tie app. We probably need our scope because we're going to do the find type. I sound so sad. Okay. And that's going to be what we return. And let's take this away. We can come down here. I said we're taking a type application and a scope. I was calling this tie app for better or worse. It's calling this scope ID. Eval type application. Okay, which is a type of type expression. I want to return fair. What's wrong with you? So I need to say that I can fail. So this is going to be a typer result of type ID. Okay. Wow. Somehow I put that had a, yeah, look at that little symbol. Okay. So I have this generic. So let inner self types get gen inner. And I think we match inner. And we have a lot of types that can't be. Yeah, anything that doesn't contain another type can't be here. And even optionals. So type point opt, that's going to be equal to it's a 1D point accent point opt of t. Yeah, so this is an optional, but it contains a struct. So I think this is allowed. So on an optional, it's fine. A reference likewise. Yeah. So none of you are allowed. I just want like a consistent way to fail. Let's say unsupported. I guess I could do this, type this over and over again. Unsupported. It's not even unsupported. It can't even happen, I don't think. Oh, do we complain if you don't use T? Right? Otherwise it could happen. Weird. Generic type. I just don't like repeating that over and over, but I don't want to wildcard it in case, you know, maybe it's fine. Maybe we'll wildcard it. So we'll just do, to do weird generic type. And this is impossible. We said you can't have a generic of an opaque alias. Well, what if I did like, okay, type alias opaque, my int, and that's just int, and then I was like, hey, I have a generic type here. Yeah, well, if my int can't take type parameters, then how would I pass it in? I could have something, yeah, that uses it, but that's fine. So I think this is also not a thing. That's also not a thing. An enum variant. Again, this is only happening at the definition level, I think. So I think it would just be an enum proper. Let's do that though. Let's have an enum. So we're gonna do our type result, te. We're gonna do that as an enum. Okay. T. Or E. That's valid syntax in this language. And I think that should be allowed. Let me check how long. All right, 26 minutes. Not made it very far. Ouch. Do generic instantiation of enum. Do tag instances, no. Type variable, no. An array. Array already is a generic. It's a special case. It's hard-coded in the compiler, and it already kind of works. What we're trying to implement already works for array because we've hard-coded it. So I don't think it participates either until we rework it to not be hard-coded. And that leaves us with these 4 types to support, and I think that's correct. So, and this will be generic instantiation of reference. And this is going to be generic instantiation. Didn't need to write that one because we're about to do it. So what's going on here? We have this struct, and we're going to be like for field and struct field sitter. Even like let mute. What else do we have to copy? Yeah. We're not going to make a copy. We're going to like start by cloning the fields or something. New fields. Struct fields clone. We could iter mute, right? It's a ref mute. We could be like if field type ID equals so in our case here, the most simple case is it just is the type. So we don't have equals if it's one of. So it's actually on the generic. So it's the generics params, those type IDs that we're interested in. So let generic param is going to be gen params iter find p gen param such that no, the type ID is the type ID of the field. Now I understand we have easy mode and then we're going to have hard mode, i.e. 2, which is going to be not a box of T, that'd be like mega hard mode, just going to be a, let's say a T optional. So that's actually not going to be equal to T. We need to like, we're going to need to write something recursive that replaces all contained types. But we're going to do fix me, make this a recursive find replace of all the instances of gen.params of gen.params to their corresponding evald type params. So these are in order. So we have two vecs of type ID, and it looks like this. So we have the first one. I'll just do it like this, is t, and the second one is array int in our actual example. So what we can do is once we looked you up, I want to enumerate, and I don't care about the index, but I want it. So this is going to be, it's going to give us the index 2. The index is first, so like that. Now we're going to do, well, this can already be, okay, match generic param. I guess this is fine. This is a no op, and we'll write this more idiomatically in a minute. So, but if we do have one, then this, I'm going to just be explicit. Corresponding type is going to be eval to type params at your tuple, so your param index, and then your generic param still. So one thing that you can do sometimes is just like put the indexes on each one so you don't have to enumerate, but it's a waste of space, and space is more valuable than cycles typically. Interestingly enough, because of what fits in the cache is more important than how much you compute. And now we're just going to say field type ID equals corresponding type. We do the substitution. And I think this will work for just structs. By the way, this no longer works. I don't know why I made that array int. Oh, I made that array int to break it. I keep breaking our example, huh? Hey, this should actually compile now. We just can't use it. I'll leave it in there and see where we get. Oh, about to sneeze. Okay. I'm inclined to fix the compiler errors, close my eyes and like wince, and then see if this runs. So let's do that. You can't find specialized type in this scope. Okay. So and if it was a struct, and once we've done our work, what we would do is we would do let a new struct, a specialized spec struct, and this is going to be a struct, struct type. That's the one. Fields, new fields, that one's easy. AST node, and this is going to be, okay. So where in the source code was this type created? This type was created not up here, not here, but actually here. This is the code that caused this to be instantiated. So we're going to do the type application expression span, parsed ID, type applications. I need its expression ID actually. Uh-oh. This comes down to me being a bit inconsistent with how I represent. Yeah, so I have this. So what I can do into this function, I will not pass the type. I will pass its ID, and this is going to be a expression ID. Parse type expression ID. Wait. No, yeah, that's what I need. And this is going to be let type equal ast get type expression. Type expressions get type ID. And this means I do my own borrow of it, which kind of helps with code organization, but it means I have the ID, which is the most important thing. And then that's just going to be, we need to expect. So this is parsed type expression, type application. It's actually inside here. Else, panic, expected type application. Cool. That's annoying. Type ID. Sorry. What else do you have? Fields, type def and info. Type def and info. This struct type doesn't have any def and info. It's just a monomorph, an instant, a created, an instance of this defined type. Dot into. Yes. Thank you. That there is our specialized type ID. Boom. Let's go to the errors. So we have our stringifier here. So type generic. Really don't know how I want to do this. I guess we can expect it to have gen info. I actually changed my mind about how I want to stringify these as well. In fact, like we might. I'm really debating just using the name. Is that right? Okay, so for a generic, Yeah, like we want to spit out the type parameters and stuff. Um, and it has a def info on it. So it's going to be a little bit like this. And so the name, and then for each param, this doesn't print constraints. Oh. Well, that's kind of nice. Sorry for the silence. We're just trying to pretty print this thing. What I want it to ultimately look like is box, t, and then parens, and then that's how this is the string that I want for our type in our example program up here. I have like some is last stuff going on. You. Okay. How big is this generic struct? I think we may just have to clone him. He's got his params, apply Ds. There is a vec. It's not small because he has this guy too. So the problem is we're borrowing from self.types, and then we're calling eval type expert, which requires a whole exclusive reference to self. So the key might be just not to use gen again, or do this thing. Oh yeah, we don't actually need it. Oh right, but I wanted to check first before evaluating. I could just get it again. Do I do the inefficient thing just for the borrow checker? Still using tie app, we're gonna clone probably. We're just not gonna be able to borrow anything as long as we have that. It's really unfortunate. I tried refactoring the whole thing such that functions like this wouldn't take mute self. They would take only what was needed, but every function was taking like 13 parameters, and it didn't actually end up helping for a reason I forgot. But we're just going to clone the thing. And then if we profile one day and there's a lot of clones, we'll worry about it, I guess. Okay, so we already self.types get type ID. No, find type. Okay, yeah, the inner is generic type, so we don't need that. Specialize the type if we haven't yet. I don't think that's correct comment, because I think anytime you have a type application, you are doing that. And then if we haven't yet, it's just going to be down to our add type being smart enough to say, hey, you already have box event. So worry about that later. You can even make it a no commit. No commit. Ensure specializations are deduped by add type. Okay. So we changed it to take the ID. We need to pass the ID. That's called type expr ID. I'm going to lose track of this special case one day, but the good news is all I have to do is search for the string array. So it won't be that bad. Really? Uh-huh. Okay. That's wrong. Oh, because we made the generic, but we didn't update eval type to actually make one. Here. Type application. No. Eval type defen. Where did we do the stuff with the generic scope? We did it up here. Right. So we add a child scope, and that's all we do. We didn't change anything. We add a child scope. I mean, we add the things, and then we eval. And then what I actually need to do is, just like with an opaque, I need to say if there were type variables, we're actually inserting a generic. So I'm checking if if it's an alias. I think I want to say that's mutually exclusive with doing generics. Is that right? Simple type alias. map a string map. So it'd be like string map where the key is always a string, T, right. And that's map string T. String map, right, type A string map T. And that's just a name for a generic. No, it's weird. It actually, for what I'm doing to work, I think I need that to also make one of these new generic wrappers. Well, let's see, because I would just look up the right-hand side, which would be a generic. Hmm. I just don't know how this interacts with the little alias system I've created. I think it's just mutually exclusive. And if you want to do that, you do that. Okay. So this is going to be if what were the params? Has type params. And I'm going to make this an else if, so we never do both. Make generic. So it's a lot like opaque alias, so I'm going to copy it optimistically. That's fine, actually. It's usually called asked ID on the thing. Enter. That's right. And the type def and info, so we just need our params. I already walked them, so I probably should have made them here. This is cool. This is cool because now I actually have somewhere to store the ID of the type variable that I was already making. And it should have been a hint that we probably didn't have all the info we needed because that we were throwing this away. So I like that this type variable ID is now getting captured here. And params is actually type params. No, this needs to happen before eval because we need to put them in scope. Make a generic. Generic. Gen. I've been calling it gen. Keep calling it gen. Okay. Whoa. I was gonna say we got to the bottom. That's amazing, but now that I do phases and stuff, it doesn't actually mean that we really got to the bottom. Okay, but look. A generic wrapper for a box. And here's our print that we did. Maybe it's not. No, that's just the right-hand side. For a... Oh. We shouldn't have passed the defin info. The defin info is on the inner. And result. It's still not bad though. If it's an alias and it's not opaque, we don't pass defin info. So what I was doing before, wait, shouldn't have been passing it because this is not an alias. But the right-hand side knows about box. Well, I can just and past defin info. We'll just do this. Make sure we're not passing it. No? Oh my gosh. Because it's an option. And we're passing. I want to be logging this for the opaque case anyway. Let me just dbg type defin info. Past type defin info. That might be good enough. Nope. That moves. Okay. So this goes, they go together like this. Look, it went away. Okay, so we did get rid of it. Generating a generic wrapper for a value t. Yeah, that's correct. Why was it an alias? Sorry. This is just a little bit perplexing. Okay. Sure. And then it's always false. I don't know. Oh well. I think this is good. And then it ran. Wait, it ran? No. No. Assert b dot value equals 1. We should get an assert failed. Which we did. And now let's try 0. Wow. So we're not done because we hard-coded the heck out of this part because we only did structs and we only did the easy case. So let me illustrate. If we had t optional here, box of int would mean that value needs to be an optional int, and we're not handling that, so we're not going to replace it. And look, so because we didn't replace it, our specialized struct is actually the same as the generic one, so it is generic. And on the right hand side of this statement, our type checker is going to be looking for a t, an optional t, which we literally cannot create because there actually is no type variable t around. So this is going to be impossible. So like this will never type check. We'll never be able to get past it because, you know, we really should be failing here. Like, hey, I failed to specialize it because I did no substitutions. Now, this is where I was getting into, hey, there is a type variable t, but it's unused. And that's kind of interesting. I think it's going to say, hey, 0, but expected unit, but got int. So this might even work fine. Okay, function main is now returning unit. That's not going to parse. But yeah, so that works. So maybe that's okay. It's maybe a warning at best. Maybe we make it a failure, but that's where we are. I guess this is another case. That one's going to trigger weird generic type, I think. Sorry. Just have to fix the parsing. Weird generic type. And that's actually because it's should be type variable. And now that I think about it, this might be allowed and this might be our even most trivial case. Generic instantiation of naked type variable. In this code here, where we match on type is going to end up being in the recursive function that we call. So this is actually going to probably end up being our base case. It's going to be this type variable case, where we actually, that'll be the only place we ever actually do substitutions because we will have walked down the container types all the way down to actually finding a type variable. But if I run this, I think we'll get the error for that is where we got. Yeah. So the to do is to take this, pull out the match on this type. We're kind of where we started at the beginning of the video, where we need to specialize a type and we're not sure how, but we actually are a lot further than that because we did specialize a single case and we added plumbing that we didn't have that we need to do so. So I think it's pretty straightforward from here. I think it's neat that this just compiles, even though it doesn't quite work yet. And I'm honestly really impressed. I guess we should look at the LLVM to wrap this up. We should see box event. Let's see if we can do that. So this is going to be in the out. We have struct generic. So the reason I can't search for files that are get ignored. So that's why I'm doing this like a barbarian. Let me go back to the version that was working. Okay, so we're not seeing a type defin up here, I think because we don't have a defined struct. We have the generic, which then gets instantiated. So do we see box? We don't see box anywhere. So we're gonna have to be, yeah, so it just gets optimized all the way down to returning. Returning 0. Even our assert gets optimized out. Yeah, sure did. And here our assert gets inlined. So it knows that it has to print assert failed. So statically, this is pretty neat. Statically, because we're using LLVM, hooray, the optimizer knows that this is going to crash right here. And so it just says, hey, I'm just going to inline assert failed. Interesting that it returns 0 because that is 0. If we put 42 here, it'll return 42. Sure will. I love how that updates live. 41, watch it. Just watch the machine code. It's not machine code at all. Watch the IR update. All right. So let me turn on no optimization. Yeah, so we're going to cargo run help. I just want to make sure. So this is going to be no LLVM opt. Debug is off. And I want test. Oh, it's just struct generic. Okay. And we're not even going to run it. Oh, no, I did run it. Hey, it's back. Okay. So what we really want is to see that B is actually a struct with an int inside it. And it looks like it's exactly that. Let's make a C with a bool inside it. Oh. Run our non-optimizing version. Here's C, and that's a struct with a bool inside. So completely different types. This is awesome. Really proud. If we dump module, and go look at our types, those are variables. We have value and value bool. They happen to be instantiations of that generic, but I actually don't say that they are. That's probably a problem. I think that they probably need to reference their parent type to say, hey, I'm an instantiation of box. Not here, of course, but that would be like in typer. Might be even on root type. So we would have to put it on every type, but it would be some information about its parent. Or what we could do is we could store it in types. So struct types, yeah, this is a defin mapping from parsed type defins to types. What we could do is we could do some specialization records. And that could be from specialize to parent, something like that, so that we could at least look up by type ID, hey, is this a specialization of another type? So we don't lose that info. This looks to me like we've kind of just lost the info, which may or may not matter. It'll probably matter because we need to be able to call the methods from box. So if I do this, we need to be able to put like a thing that gets the value out and returns a t as a method on there. So we're going to need to know. But anyway, this is really neat. If I do 2 boxes of bools, what I want to see is only one type. Wow, that was really long page back history. Yeah, because actually we're just inserting a struct. So our struct equality check already works. It's the same struct as one we've already seen. We may want to turn that off so that we know the difference between an anonymous value bool struct. So an anonymous value bool struct and one that was instantiated via box. So that stuff that box is supposed to have, like ability implementations or methods, will work. Just thinking out loud, still much to do, but I'd say well on our way to having generic types, which is, you know, a blocker for hash map, which is something that I really want to get implemented here, and then a few other things, including this result type that I'd like to implement mostly in user land and just do syntactic sugar as built-ins. If we go to the project to-do list, quite a bit. I know it's just here. Slices. I think slices, there may be some other things I don't have here, but in particular slices I think depends on the generic types. And I do want to have slices in the language. So anyway, that's enough rambling. Really appreciate, as always, if you did watch this video all the way to the end or even parts of it. I hope you learned something. Yeah, I'll see you next time.